Hello, everybody. So what we're going to be looking at today is section 1. No, try again. Section 4.4 in your book, which is going to be on tangent planes and linear approximation. So this is a nice, easy section. Should be pretty short. Yeah, and we'll go ahead and get started. So what we're going to be learning in this section is how to do two things, basically. We're going to learn how to determine a tangent plane to a surface. That's what we'll talk about first. And then we'll just talk about how to approximate a function using a tangent plane, which is also very easy to do. So yeah, pretty straightforward. You're basically going to learn, almost just one thing really this in this lecture. And let's go ahead and get started. So first thing is, what is a tangent plane? And hopefully this picture here will answer those questions, right? So what you've got going on here is you've got this surface, right? And then if you pick a point on the surface, there's going to be a plane that is tangent to the surface, right? So just like you have in 2D, the concept of a tangent line, right? In 3D, you have the concept of a tangent plane, right? I think in the last lecture I said it's like if you have like an orange and then like a piece of paper sitting on the orange, then that's like a tangent plane. So that's what's going on here. Of course, what we want to know is how to calculate them and that kind of thing, and we'll have to derive that really. So yeah, so let's just mention something about calculus 1. So also let's say tangent planes. So it's written somewhere. All right. So in calculus 1, first you find out what the slope of a tangent line is, right? You find out that f prime of a is the slope of the tangent line, or the curve, you could also say, at the point a comma f of a, right? Well, in calculus 3, it's a little bit different. So in calc 3, with a function of two variables, x and y, f of x comma y, we've already learned that there are two slopes we can calculate from here. There are two slopes we can calculate. Right? So in the previous section, we learned that like f subscript x, the derivative with respect to x, the partial of f with respect to x, evaluated at ab is the slope in the x direction. And we also learned that fy, that's subscript y, but the page break here, is going to be the slope in the y direction. Now, what does that mean in terms of the tangent plane? Well, let's go look at this picture up here again. Now, this picture is not like on any kind of axes here, and they actually drew this picture in your book for another reason. They were trying to justify the idea that there was a tangent plane, and I'm not really doing it at this point. But let's just say that, let's just imagine that there's like a set of axes on here. Just change that a little bit here. Like, let's say that's the x-axis, and then let's say like, I wanted that to be a straight line. Hold on. There we go. And let's say that's the y-axis, and let's say that's the z-axis, right? So I'm just drawing little axes here, and then let's say this is our picture. Now, this tangent plane there's a couple of vectors that we can look at here. So you've got this point right here. That's the point we're going to be concerned about. And the idea here is that this tangent plane can come from two different vectors. So you could find the slope in this direction. Let's say that's the x direction. That's kind of what I was trying to draw here. So let's say this is the x direction. And so like this vector could be tilted down or it could be tilted up, right? Like it could be this way or it could be this way, just depending on what's going on. But it's the slope in that, there's a slope in that direction. Now, in this direction, obviously this tangent plane is tilted, down, obviously from left to right, right? So there's a vector there as well. And this would be perhaps the slope in the y direction from that point. Okay, and so those two vectors that I drew here, this blue one and this green one, those are really going to be your, they're going to be vectors that we want. And they're not actually fx and fy, because fx is a number and fy is a number. Okay, so that's not what these two vectors are on this graph. Okay, what they are, though, is the following. So if you were trying to figure out this vector here, what it's going to turn out to be is, so that blue vector, let me get a blue color again. So the vector in the, I'll say x direction, the way you would get it is from that derivative. So if I'm writing x, y, and z components for this vector right here, first of all, if it's in the x direction, and then it's either up or down, then the y component of that vector is going to be 0. Okay, and the x direction, well, we got to look at it. And so if you were carefully looking at this vector on a 2D plane, you might see this. So like if you look at just the x and the z, then what you would see is that from like 0, 0, the vector might point up or the vector might point down. You don't really know what it's going to do, but what you do know it's going to do is that it's going to be like if fx, for example, this is just an example, if fx evaluated at the point is, let's say, 4, then that would be a slope, right, in the x direction. And what that would mean on this little graph that I'm drawing here is that the slope is 4. So if a slope is 4, what that means is that the rise would be 4 and the run would be 1. So it would be steeper than I drew it, but like that's an example. So you calculate this derivative, it's 4. That would mean on this xz plane, the slope is 4 for this vector. And so if I'm writing a three-dimensional vector for that, what it would mean is that the x component is 1 and the z component is 4. Okay? Hopefully that makes a little bit of sense. And then the idea here is that, of course, you're going to be calculating this, right? It's not always going to be 4. That was a made-up number. But whatever this derivative is, the fx evaluated at AB, that goes here. So what's going on is that this vector has no direction in the y, has no y component because it's not pointing in the y direction at all. And then its slope is fxab over 1, right? Because we said that this is the slope. So if you put it over 1, it's still a slope. So that's a little bit convoluted, but it's more than the book does there for justifying that this is going to be this vector here. Now the green vector, the same thing is going to be going on. So the vector in the plane in the y direction, same idea. since it's not pointing in the x direction at all, the x component is 0. And then its slope is Fy AB, which would mean that the z direction is FYAB and the y direction is 1. So it's the same picture that we drew before, where except if I put a y and a z here, you've got some kind of vector. And the y component of that vector is, sorry, the z component of that vector is FYAB. And then the y component of that vector is 1. And then that way, if you do rise, if you do rise over run, you just get Fy over 1. And that's why that middle component is 1. So again, just to justify, I'm going to say it one more time because this is confusing. The vector that's in the x direction has a 0 y component. The vector in the y direction has a 0 x component. That's because, like, if this vector is pointing in the x direction, it's not pointing, this way. It's not pointing to the left or to the right of just the straight x direction. This should be pointing exactly parallel to this. And this one should be pointing exactly parallel to this. It could be tilted up or down, but it can't be tilted in the x direction at all. So that's why you have these zeros. And the fx and the fy are slopes, but you can think of them just as slopes in a 2D plane because we threw out one of the variables already with it being 0. So if you're looking at what's left, this is going to give you a slope of fy, and this one's going to give you a slope of fx. Okay, hopefully that's not too complicated here. Okay, so we have these slopes. That gives you these two vectors. So in the tangent plane picture we have, in the picture above, we can find two vectors that are supposed to be in that tangent plane. And we don't really give them names, but we're just going to write the vectors. So one of them is going to be what we just said, 1 in the x direction, 0 in the y direction. And in the z direction, you have fx evaluated at some point. And the other one is going to be 0 in the x, 1 in the y. And then you get your slope in the y direction in the z component. Okay, so you end up with finding these two vectors. Okay, and they're just the two that I drew in that picture, the blue one and the green one. Once you have those two vectors, then what would we need in order to find the equation of a plane? We did talk about the equation of a plane a little bit, didn't we? You need a normal vector, right? To write the equation of a plane, you need a normal vector. Okay, just kind of a warning at this point, because I realize I haven't given you a warning. We're deriving a formula. You're not supposed to compute tangent planes this way. Don't compute tangent planes the way that we're doing it right now. Okay. I mean, you can, but you probably shouldn't. Okay, so that's just a warning before we go on. You're not like supposed to be following this method. We're going to calculate some after this. So we need a normal vector to the plane. If you have two vectors in the plane, like I drew, then where would the normal vector be, right? The normal vector would be from this point pointing straight out of the plane, which is hard to draw the way this one is, but like maybe like that. And then this has to be a right angle and this has to be a right angle. But it's hard to see that this and this are a right angle just because of the angle of that plane is a little bit weird. Uh, on this picture, right, the idea is like if you have a plane like that, or if you have a vector like that and a vector like that, then the tangent plane, the normal would be like that out of that plane. Okay, so you need that normal vector. The way you calculate a normal vector usually is if you have two vectors in the plane, you can do a cross product to find an orthogonal vector. We know, I don't want that color. You can use a cross product to compute the normal vector. Right? And so as long as you have two vectors in the plane, which we do have two vectors in the plane. So our normal vector is going to be this. Normal vector is going to be those two vectors cross product with each other. So one was 1, 0, fx. I'm just going to write fx instead of fxab. And then cross 0, 1, fy. And that's how we're going to get our normal vector. Now, we actually have to perform that cross product. We'll just do it by hand here. ijk, 1, 0, fx, 0, 1, fy. So we're going to perform this cross product. So we've done that a few times. So it's going to be I times, let's see, 0 fx, 1 fy minus j, 1 fx, 0 fy, plus k, and 1, 0, 0, 1 looks like. Let's see here. Oh, they reversed those from me. Okay. Do I want to do that? Yeah. Okay. I'm going to keep it the way it is just to avoid rewriting it, but let's just finish this out. So if you finish this cross product, then we got to do the determinants of these little 2x2s. So for the first one, it's going to be I, and then 0 fy minus fx, and then minus j, and then you have fy minus 0, and then you have k, and that's 1 times 1 minus 0 times 0, so just 1. All right, and so if I write it in this triangular bracket notation to make it easier to look at, we'll have negative fx, here negative fy, and then 1. Okay, now just by convention, I want to match the way your book did this. And so in order to match the way your book did this, they don't use this as their normal vector. They so when you calculate a vector, right? Like if you have this normal vector here, you could have also used the one pointing in the exact opposite direction, right? That's also a normal vector. And it turns out that that's what the book does compared to what I did. So we've got this vector here, but just the book happens to use the opposite direction vector in their formula. And the reason they do that is so that they don't have these minuses here. So your book uses fx, fy, -1 instead. And there is a reason for wanting the signs that way. We'll use what they use just to keep it nice. Okay, so having said that, let's continue on and let's write the equation, the tangent plane. So let's do our setup here. So we have so suppose we have z equals f x y. That's going to need to be, have derivatives that exist and everything. Needs to be differentiable because we're taking derivatives. Okay. And we have a point where we want to compute the tangent plane. And I'm just going to say x0, y0 instead of AB. All right. And so that's what we want. We know that in order to compute the tangent plane, we need a normal vector and a point. Okay. So we will use the point. What kind of point do we use? Well, it needs to be a point in space. So x0, y0 is not quite a point in 3D space, but what we would do is the x coordinate for the point in space is x0. The y coordinate is y0. And if you want the z coordinate, you'd have to plug this into your function because you calculate z values from the x's and y's. So if you want the z value that goes with this, you have to plug this into your function. So it'd be f of x0, y0. That would be your point. Okay. Now your slope, you don't have a slope, you have a normal vector. And we're going to use the exact normal vector that I said we're going to use, which was in equals, and it was fx, fy, -1, but specifically those need to be evaluated at the point. So like fx at x0, y0, fy at x0, y0, and then -1. Okay, because you need numbers there, right? So if you don't plug in the point, you're not going to have numbers in general. Once we have a point and a normal vector, then you can write the equation of the plane. So, and then the plane is, well, we know the equation of a plane. If you remember, it was a x minus x0 plus b y minus y0 plus c z minus z0 equals 0. And the ABC was your normal vector, and the x0, y0, z0 was your point. So if we fill in our information, the a is the x component from your normal vector. That's here, right? Let me just label this actually. So this is your a, this is your b, this is your c, and this is your z0, which we'll need right here. So you fill those in for a, b, c, and z0, and we are going to get a, which is, so fx evaluated at x0, y0, x minus x0, plus the b, which is fy, x0, y0, y minus y0. Going to need more room. Move this. Let's put this back. Okay. Your z component, you got c, which is just -1. So this is actually just minus z minus z0. The z0 is f of x0, y0 from this right here. Okay, and all of that is supposed to equal 0. Okay, so then what they do is they simply take the z here and they move it to the other side. Actually, let me not do that. Let me erase this. Let me put this equal 0 on the other side. And we're going to take the z and it's going to go over there. Okay, so if we move that to the left, what's going to happen is you're going to end up with, this is a negative z. So when you move it over to this side, it's going to be a positive z. Then you've got, if I just continue on from right here, you have a negative negative f of x0, y0, which it's positive because it's negative negative. And then you've got these two terms. So I'm just plopping those down. And this is your formula for the equation of a tangent plane that's just all worked out for you. And you just need to plug stuff in. So this is the one that you usually want to use because you just plug in all of your numbers basically. Okay. That way you don't have to do like that cross product every time and that kind of stuff. Okay. Let's just do a few of these to get started and we'll see how this goes. And then we'll talk about it more uh, deeply, I guess. So let's do an example. Find the equation of the tangent plane to the surface defined by, and then we have our function. So they can just give you any function of x and y here, as long as it's differentiable at the point where they want you to do this. So we have 2x squared minus 3xy plus 8y squared plus 2x minus 4y plus 4. And we need a point where we're doing this at. So then they say at point 2 comma negative 1. Okay, so here's what they want us to do. We just need to find the equation of the tangent plane. So if you look at what you have here, basically we just need a couple of things. First of all, we need the derivative evaluated at the point for x, the derivative evaluated at the point for y, and also you need to know the function value evaluated at the point. That's basically what we need. So let's say that and then let's do that. Okay. So basically, for our formula, we'll need to compute the following. We need f of 2 negative 1, because that function value is used right here. And then we need fx and fy also evaluated at that point. Okay, so those are the three numbers that we need to calculate, and then we can just write our equation, okay? So we'll just do them one by one. So let's just start with f of 2, 1, because that's going to be the easiest to compute. So f of 2, negative 1, there's no derivatives there. We're just plugging that back into the original function. So you plug 2 comma 1 in here. So you have 2 squared minus 3 times 2 times negative 1 plus 8 negative 1 squared plus 2. Wait, why is that right? Hold on. Yeah, I guess it's right. Minus 4y, y is negative 1 plus 4. Okay, so we just work this out. We're going to get a number. So we have 2 times 2 times 2, so 8. Minus 3 times 2 times 1, well, negative 1, so that's going to be plus 6. This is a plus, I think. So we got plus 8, another plus 8, plus 4, plus 4, plus 4. All right, I guess that's it. So 8 and 8 is 16, 22, 26, 30, 34. Let me just check that because I can. Is that 34? Yes. Okay, so that's the correct answer there. So we needed that number. Then we need those two derivatives. Now, in order to calculate those two derivatives, of course, we need to actually do some derivatives before we can plug in numbers. So let's compute fx and fy. I guess we'll actually do fx and then plug in, and then fy and then plug it in, because why not? All right, so let me steal this function so I can just look at it while I'm doing my derivative. Duplicate it, move it down here. Okay, good enough. All right, so we're going to compute fx just for x and y first. So that means the x derivative here. So you have to remember how derivatives work, partial derivatives work, which is we treat any other variables as if they were constants. So we're taking the derivative with respect to x right now. So the derivative of 2x squared is simply 4x. The derivative of negative 3xy, we're treating the y and the 3 like they're constants. So the derivative of negative 3xy with respect to x is negative 3y. That's the kind of derivative that feels wrong, because like you're writing a y, but you were doing an x derivative, but that's correct. Then you've got the derivative of 8y squared, that's 0, because there's no x's. Then you have the derivative of 2x, which is going to be 2. The derivative of 4y, which is 0, because again, we're treating y like constant, so it's a constant. And the derivative of 4, also 0, because it's a constant. So this is what we get. Now we got to plug in our point. So we know to plug in 2 comma negative 1, we're going to get 4, 2 minus 3, negative 1 plus 2, which is 8, plus 3 plus 2. So I think that's 13, right? So fx 13, f 34. All right, so we're going to move on and we're going to do the y derivative. Let's move this a little bit out of the way again. We also need fy, so fy of x and y. So now we're going to go back and do a y derivative here. So the derivative of 2x squared is 0 with respect to y. The derivative of negative 3xy with respect to y is negative 3x. The derivative of 8y squared with respect to y is 16y. The derivative of 2x with respect to y is 0. The derivative of negative 4y with respect to y is negative 4. And then the derivative of 4 is 0. So we're done with this. And let's plug in our point. So fy evaluated at 2, negative 1 is negative 3 times 2 plus 16 times negative 1. So we have negative 6 minus 16. So that's, and then minus 4. So it's negative 6 minus 16, which is negative 22, minus 4, which is negative 26. That is that. Okay, so we have our pieces here, the 34, the 13, and the negative 26. That's everything you need for your equation of the plane. So the plane now is going to be, well, let's write the formula. I'll just write it instead of copy pasting it. It was z equals f of x0, y0 plus fx x0, y0, x minus x0 plus fy x0, y0, y minus y0. Okay, so we just plug in our numbers. So we have z equals f of x0, y0, right? Well, that was the first one we calculated. It was 34 plus, then we've got our fx derivative, which was this one, 13, and then x minus x0. What's x0, right? Remember, the point, the x value of the point is 2. So that's x minus 2. Then we got this one. So we have plus fy, 2 comma negative 1. Fy was negative 26. And then y minus y0 is y minus the y value, which is negative 1. Okay. And this is basically it, but you can also do a little bit of simplifying. Not too much, but you can go 34. And then, you can basically just multiply this out if you want to. So you'd have like 13x minus 26. And then here you'd have negative 26 times y, so negative 26y. And then this is obviously minus minus 1, which is 1. 1 times negative 26 is negative 26. So if you combine all your like terms, you've got 13x minus 26y. And then if we add up all those constants, we have 34 minus 26 minus 26, which is negative 18. And so that would be kind of your simplest looking equation of the plane. And this is what you would calculate first. But they're both the same plane. And that's how you go about it. Okay. Now, something I'm going to mention that you're not going to have to do in the homework. But the reason you're not going to have to do it in the homework is because of a mistake in Newton Alta. Okay. So Newton has a topic, compute the normal to a surface at a point. Okay. Now that was exactly the normal that we have calculated previously and then used in that formula. So if we scroll way up here, this was what we calculated. This was what the book had. And this is literally what they wanted you to calculate. And I'm just going to mention it, write it down, put it in a box, and you're not going to have to do it. And it's because the problems that were in Newton were actually literally unsolvable. So you can't do it. But I'm just going to comment on it. So Newton has a topic, compute the normal to a surface at a point. And you would need to know the formula. So idea, the normal vector in to a surface z equals f of xy at point x0, y0 is n equals, and it's what we wrote down. It's the derivative in the x direction evaluated at the point, the derivative in the y direction evaluated at a point, and then negative 1. Or this vector upside down, but we don't count that. Okay, we have that. Due to Newton's mistakes, this is not on your homework. And I'm going to say not on the summer 2021 homework. Who knows? Maybe somebody will watch this video later. Yeah. And so basically, I'll tell you what they did too, because it's super annoying. What they did is in about over half of the answers to their questions, they just left this spot blank in the official answer with no negative 1 there. And the problem with leaving that blank is, first of all, it's incorrect. But second of all, like when you're doing your homework, you can't actually leave it blank and hit submit. It won't even take that as an answer. So it just makes it completely unsolvable. Which is why if you look at your homework, it'll say version 2 because I had to make a separate homework assignment. And then there's one poor student who did half the homework assignment and has to redo it now. I guess technically he doesn't, but probably he will. Anyway, so that's just a comment there. I wanted to give that a shout out to that particular problem type, just in case. Okay. Let's see here. I mean, that's the main thing. I want to, let's see if we do a linear approximation here. So in calculus one, we'll do, we're going to still do more of these. So linear approximation. In calc one, you did this. So you got a function, and your function is just whatever function it is. Maybe it looks like that. You've got some point on here, a, come up there to the a, and of course that point is a comma f of a. And then there's a tangent line there, like that. And that's your tangent line. And what you learned was that if you're close by to a, then the tangent line and the original function are close together, right? Like if you just look in a small section of this graph, like right here, aren't the red curve and the green curve just really close together there? They are, right? So that was the idea of an approximation. These two things are close together. So the idea was if x is close to a, whatever close to means, that's why I put it in quotes, right? If you're close to a, then f of x is approximately equal to its own tangent line, right? Like the red curve is the tangent line. So the red curve and the green curve are close together, but only around a. So we have that. And then what is the tangent line? Well, the tangent line had a formula like this: f of a plus f prime of a, x minus a. All right. That was the idea. And we want to extend that to the, functions of two variables, and we will. So let's go still this picture. No, we can't still it. Let's make a new picture here. So in calculus 3, it's the same idea for functions of two variables. Let me put the picture of a tangent plane on here again. Make that a little bigger. So the idea here is if you just kind of highlight a little section, like if you, that's not highlighting, if you highlight a little section around this point here, right? In that section, the tangent plane and the actual curve, not curve, and the surface are close together, right? So the surface is the orange shape and the plane is the flat one, obviously. And like in the area that I highlighted, they're going to be close together because actually at this dot, they overlap, right? And then the further away you go in any direction, the further apart they get. So like basically you have like that kind of thing, and just say if xy is close to x naught, y naught, right? That's where we're doing the tangent line approximation. Then f of xy, f of xy is approximately equal to its tangent plane. All right. So it's exactly the same idea. So in symbols, though, let's figure out how to write this. I didn't really leave myself a lot of room. Move this over here a little bit, make it a little bit smaller. This over. Okay. All right, so I think that's good enough. So we can say it this way. So we will say, given function with continuous partial derivatives, so given z equals f of xy with continuous partial derivatives, right? Because you have to take derivatives to find the tangent plane. At a point x0, y0, we could say two things. Number one, the linear approximation of f of xy at x0, y0 is, we call it L of x comma y, and it's just going to be the equation of the tangent plane again. So like, let's look at the tangent plane just to remind us what it looked like. Where is it? Where? Okay, here it is. Right. So this is the equation of the tangent plane right here. And what we're going to do is we're just going to say, well, instead of calling it z, we're just going to call it L of xy. But this part, the actual part for the plane, we're just going to leave it exactly the way it is here. So we're not doing anything, we're just renaming it. And that's actually the same thing as this, because this is just the equation of the tangent line. But we're kind of like, you would call it L of x in calculus 1. Okay, so let's go here. So what's the equation of the tangent plane? It's f of xy, x0, y0, plus fx, x0, y0, x minus x0, plus fy, x0, y0, y minus y0. So there's that. And the point of it is that this if x comma y is close to, whatever close to means, we don't know, x0, y0, then f of xy is approximately L of xy. Or, if you want to write out what that is, the L of xy is the equation of your tangent plane. So it's this. Okay, so those are your definitions for linear approximation. It's literally the exact same thing that we were doing. So yeah, let us do a problem. Okay, good. So example, given f of xy equals square root 41 minus 4x squared minus y squared, approximate f of 2.1, 2.9 using 2 comma 3 for your x0, y0. I'm going to say to approximate it to 4 decimal places. Okay, so In order to do this, the first thing you're going to do is you're going to need to calculate that L of x, L of xy, which again is just the tangent plane. Okay, so in order to find L of xy, we're going to need f of x, like f, fx, fy evaluated at the point. So we're going to need, we need f evaluated at 2 comma 3, right? And be careful that you understand this, right? You're approximating this value. These are the ones that you're actually using to calculate your plane. You use this one first, and then we plug this in later. Okay, so we need f of 2, 3. We're going to need fx of 2, 3, and we're going to need fy of 2, 3 in order to find the L of xy, right? So let's just kind of move these out of the way, maybe. Actually, we can just probably delete them. No, you know what? Let's leave them. Hold on. Hold on. I want them somewhere, but I don't want them taking up so much space. Okay, so let's do this. We need these. So the f of 2 comma 3 is plugging 2 comma 3 into the function. So the original function is right here. So just plug in 2 comma 3. So you have square root 41 minus 4x squared minus y squared. So that's square root 41 minus 4 times 4 is 16 minus 9. So what will that be? It's too late to do math. I'm just looking for a calculator. Oh, it's 16. Okay, cool. Yes, I just went and picked up a calculator just to avoid subtraction. Okay, so there you go. Next thing to do is we're going to need the fx of 2, 3. So we need fx. So we need fx of xy to start with. We're going to have to take a derivative here. Now, just, remember from Calculus 1, hopefully you do, the derivative of square root x, yes, you could use the power rule. It's a lot easier to remember this derivative to be this. And remembering that really just makes your life a little bit easier on problems like this. Because when I'm taking the derivative here of this function, I go, oh, it's a square root. So the derivative of a square root function is 1 over 2 square root. Now you have all of this stuff inside the square root. And then you have to multiply by the derivative of what's inside. I'll do this in 2 parts. So d dx of 41 minus 4x squared minus y squared. Now the denominator I know is like this, 41 minus 4x squared minus y squared. And I left the numerator blank up here because I'm just going to do this derivative and put it right here. So we're going to do this derivative and put it right there. All right, so we're taking the derivative with respect to x. So what's the derivative with respect to x of 41? 0. What's the derivative with respect to x of negative 4x squared? It's negative 8x. What's the derivative with respect to x of y squared? 0, because that's a constant as far as this derivative is concerned. Okay. Now from there, we need this evaluated at, what is it? 2 comma 3. So we plug that into this function. We have negative 8 times 2 over 2 square root 41 minus 4 times 2 squared minus 3 squared. So that's negative 16 over 2. And we just did that square root, right? Like this square root is the same as this square root. I know that the result is 4. So negative 16 over 8, which is negative 2. Okay, so we have this, is 4. This is negative 2. And now we got to go to the fy. So fy, we're going to be taking the same derivative, or sorry, we're going to take the y derivative of the same function. It's going to look exactly like this, actually. The only difference when we're doing the y derivative is that for the chain rule part, right, we're actually doing a y derivative now. So just like before, I know that the bottom is going to be 2 square root 41 minus 4x squared minus y squared. This can go right here, but this time it's a y derivative. So the derivative of 41 is 0, the derivative of 4x squared is 0, and the derivative of negative y squared is negative 2y. And then we can plug in 2 comma 3. So we're going to get negative 2 times y over 2, and then we've seen that 4, it's a 4. So we have negative 6 over 8, or negative 3/4. Okay. Now what? So once we've calculated this, wait, sorry, there's a weird number here. Let me just see what's going on. No, this is all fine. Okay. So once you have those all calculated, right, we can write the L of xy. So let's do that. Oops. So L of xy is, we got to write out the, I don't want to write out the formula again because I'm tired of writing out the formula. I'm just going to put in the numbers, right? So it was f of xy, which is 4, plus, in this case, minus 2 x minus x naught. The x naught is 2, plus fy, which is negative 3/4, y minus y0, which is 3. So that's your tangent plane, right? So that's the tangent plane equation right there. You could multiply this out. Your book multiplies this out. You shouldn't unless you need to, right? Don't simplify unless you're required to. You'll see why momentarily. Okay, so we've calculated this linearization. That's not actually what is said to calculate. We want to use the linearization to actually approximate this value, okay? So we got our linearization done. Now we want to use the linearization to approximate f of, what was it? It was f of 2.1, 2.9, right? And so again, the whole idea is that f and L are close together. So we know this, right? So we know that f of xy is supposed to be approximately L of xy, right? So when you're doing this problem, what you do is you say f of 2.1 comma 2.9 is approximately L of 2.1, 2.9. And that can be calculated from your L, right? So you're just going to plug this into L, right? That's all you're going to do is you're going to plug 2.1, 2.9 into L. L is up there on the top of the screen. So let us just do that. So you put in the 2.1 and the 2.9. So 4 minus 2, 2.1 minus 2, minus 3/4, 2.9 minus 3. Now, up here, you notice I said don't simplify unless required. You'll see why in a minute. Here's why. This right here and this right here are very simple calculations, and they're simple because we didn't simplify a few steps ago. Okay. These are easy to do like by hand. Oops. Because we didn't simplify. So those are easy because we didn't simplify L of X. Okay, so just keep that in mind that that's why they're pretty nice looking. So like I'm not even using a calculator at this point yet. So I have, oops, stop moving. So I have 4 minus 2 times 0.1 minus 3/4, which I'll write as 0.75. And then 2.9 minus 3 is negative 0.1, like that. And again, I'm not even using a calculator here. I can do this by hand because this is 4 minus 0.2 and then plus, and 0.1 times 0.75, that just moves the decimal place over 1. So you end up with 0. What? Oh, 0.1 times 0.75. So that's going to be 0.75, like that. And again, that's actually doable by hand. My brain is tired and I'm actually typing it into a calculator if you care, but um, okay. So where is my answer? I just want to check it. Oh, I typed that in wrong. Okay. Problem solved. So that is approximately 3.875. Okay. So make sure we understand what this value is. So what we're saying is this. So we're saying f of 2.1 comma 2.9 is approximately 3.875. That's not exact though, but it should be close. If you care, I'll actually tell you what the exact answer was, so you can compare it. The exact answer actually was f of 2.1, 2.9 is equal to, it's the square root of 14.95, which is like 3.8665 something. Okay. So that's pretty close, right? Like we calculated 3.875 and the actual answer is 3.8665. So the 3 and the 8 are correct. This is a 6. We calculated a 7. So the error is there. So it's like, less than 1% error, I think. So it's pretty good. Okay. Let me do one more kind of question. I just saw this in the homework and I was surprised it was there. And because I'm surprised it's there, we might as well do one and we'll see how it goes. So give me 1 second to find it in the homework. Should show up in the first couple questions. Yeah, there we go. Perfect. Okay. Yeah. So here's the question, and we'll see how to do it. So I'm just going to say angle of inclination. You're probably going to have to do one of these in the homework. That's it. But it doesn't hurt to understand it. So here's the type of question, and then we'll explain it. So we'll just do an example, and then I'll explain as we go. So they say find the angle of inclination of the tangent plane to the surface z equals negative 2x cubed plus xy minus 3x minus 3y cubed at the point negative 1, negative 1, 9. Okay, so let's just explain the idea first, and then we'll do this and figure this out. Okay, so the idea is this. Idea. So the tangent plane is not horizontal, generally. Right? So like if you're looking in the XY plane, not the XY plane, sorry. If you're looking at the surface, I'm not drawing the correct surface, I'm just drawing a surface. If you've got kind of some surface, let me just shade this in real quick. So you got some kind of surface, right? And you're going to calculate a tangent plane somewhere. So like, like let's say let's say right here, we're going to calculate a tangent plane. And so the tangent plane might look like this. Okay. And that's not horizontal, right? It's like tilted in some direction or the other direction. So if it was horizontal, it would be parallel to the XY plane. XY plane is the ground, right? If it was horizontal, it would be parallel to the XY plane. But it's not. Okay. And what we want to do is measure how far off of being horizontal is it. So how tilted is it compared to the XY plane? That's the angle of inclination. All right, so that's the idea. Is that it's the how tilted is it? Should be like if it was completely horizontal, the angle of inclination would be 0. But it's not completely horizontal, so it has some angle. And the way you do that is you want to find its angle compared to the XY plane. So recall the angle between two planes is calculated by the angle between their normal vectors. Right? And let's see if I can draw this. I don't know if I can. We're going to try it. Oh, already failed. Yeah. All right. So like, let's say that you have these two planes here. And so if you want to calculate the angle here, theta, that angle between those two planes is actually the same as if you had um, like the normal to the bottom plane there in one, and then you had the normal to the plane on top um, in two, that's also theta. So the angle between planes is also the angle between the normal vectors. And, depending on how well, like how much sense that picture I just drew made sense to you, maybe you believe that. If not, you can look back to the section on planes and we talked about the angle between planes. Um, so for what we need to do here is you need to find um, the angle between your plane. So for angle of inclination, you need the angle between the normal to the xy plane, which is easy to calculate. The xy plane is horizontal, right? Flat on the ground. Its normal vector is just this, 0, 0, 1, right? That's just straight up. Its normal vector points straight up. So you just need the angle between the normal vector to the xy plane, which is 0, 0, 1, and the plane that you calculate, the tangent plane. So what's the normal to the tangent plane, right? That's the one that's fx, evaluated at the point fy, evaluated at the point -1. Okay? Um, so, I mean, that's the logic of what we're doing here. We need to actually solve this. So here's what you do. So we're going to take this equation here. So let's actually solve our problem now. Solution. All right, so there's our surface. Okay, so step one, we need the normal vector to this plane. We don't need the plane, we just need the normal vector. And also we need the point, which was given to us. So the normal to the plane at, it was -1, -1, 9, maybe? Yeah, there it is, -1, -1, 9. Which we're only going to need the -1 and the -1 from it, but okay. So find the normal to the plane. Okay, so let's do that. So we know that the normal vector to the plane is calculated this way. We need those derivatives. So find the fx and fy. Now, nothing's called fx and fy, so you could call them like, if you want, partial of z with respect to x, partial of z with respect to y, right? Because it's not called f. But it doesn't matter. It's the same problem. So I'll just call it fx, even though it's not called f. All right, so what's fx? Derivative with respect to x. So that is the derivative of this function with respect to x. So that's -6x squared plus 1. Wait. Oh, it's supposed to be xy. Did I write it wrong? Okay, no, I copy pasted it wrong. It missed the y somehow. Okay. So -6x, the derivative of xy with respect to x is y. The derivative of -3x with respect to x is -3. And the derivative of the last term is 0. So we need to evaluate that at -1, -1. So -6, -1 squared plus -1 minus 3. What do we get? We get -6 minus 1 minus 3, I believe. So that's negative 10. So we have this derivative is negative 10. We need the one for fy. At first, we just need fy, not fy of anything. So fy is, where's the function so I can look at it? So the y derivative, that's going to be 0. The derivative of xy with respect to y is x. And then the last term has a y. So it'll be 2 times 3 is 9, negative 9y squared. Okay. We needed that evaluated at negative 1, 1 again. Negative 1, negative, wait. It's negative 1, negative 1. Okay. So negative 1 minus 9, negative 1 squared. That's negative 1 minus 9. So that's another negative 10. Interesting. All right. And that's all you need for the normal vector, okay? So we're supposed to find the normal to the plane. We've got those two values, and so this says that the normal is going to be negative 10, negative 10, negative 1, right? Because remember, the normal vector, the last component is just negative 1. So there's your normal vector. All right, that's step 1. Now step 2 is going to be to find the angle between that and the 0, 0, 1. So find the angle between that normal vector, negative 10, negative 10, negative 1, and the normal vector to the xy plane, which is 0, 0, 1. Okay? And then from there, you've got to remember what the how to find the angle between two vectors, right? So we got to recall the cosine of the angle between two vectors would be like u dot v over, what is it, magnitude u, magnitude v, like that. So we'll do that, but with these vectors. So you have cosine theta is negative 10, negative 10, negative 1 dot 0, 0, 1 over magnitude negative 10, negative 10, negative 1, magnitude 0, 0, 1. So we work this out. The dot product's very easy, right? Because you multiply like components. So it's 0 times negative 10, 0 times negative 10, 1 times negative 1. So 0, 10, negative 10, 0, negative 10, negative 1, 1. And then in the denominator for these two magnitudes, you've got the magnitude of 10 squared, 10 squared, 1 squared. And then you've got the magnitude of 0 squared, 0 squared, 1 squared, which you didn't really need to do that last one because, I mean, the magnitude of 0, 0, 1 is just going to be 1. But we get this. So we have cosine theta is, in the numerator, we simply have negative 1. In the denominator, we've got square root of, this is going to be 201, right? 201 times 1. So it's just negative 1 over square root 201. So then that tells us that the angle theta is going to be the inverse cosine of this, which is negative 1 over square root 201. You punch that into a calculator. Make sure your calculator is in degree mode because they, for whatever reason, want it in degrees. So just be careful with your calculator here. I'm going to put my calculator into degree mode. It is now in degree mode. And then I want the inverse cosine of -1 over square root 200, nope, just 201, close. Oh, oopsie, oopsie, mistake over here. So this is supposed to be absolute values. 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 So that's supposed to be +1. Sorry about that. Let's try it again. Cosine inverse 1 over square root 201. And I get that theta in degrees is approximately 85.95 degrees. And so what that tells you is that actually, like, I'm not going to like plot this in the correct place or anything, but almost 90 degrees, right? So it's like, it's really tilted. It's like very close to vertical. Close to 90 degrees away from horizontal. All right. So the punchline there was really kind of the logic, which is you're going to find the normal vector, and then you find the angle between the normal vector and 0, 0, 1, using the angle between vectors, because we just want to figure out how tilted is the tangent plane. Okay. So, I mean, I think we only did 3 planes. I mean, we did 2 planes and we did a normal vector. Finding the normal vector and finding the plane are almost the same amount of work. We're an hour and 22 minutes in. I think that's good for now. Yeah, I think we're good for now. Okay, so that's it for now. I will talk to you guys later, I think.